Hello, my name is Hunter Gibson, and this is my 20 LED roulette wheel, designed and built entirely with discrete components. In this project, I explored analog timing, digital logic, and transistor control to create a spinning LED display that gradually slows down and lands on a pseudo-random result. Let's take a closer look at how it all came together. I began with a simpler version. Just 10 LEDs driven by a 555 timer in astable mode and a CD4017 decade counter. The 555 timer generates clock pulses at a frequency determined by the equation F equals 1.44 over R1 plus 2R2 times C1, where R1, R2, and C1 set how fast the LEDs chase around the circle. The CD4017 then steps through its outputs one at a time with each pulse, lining up the LEDs in sequence. Initially, this gave me a great chase effect, but I wanted more LEDs for a true roulette feel. Expanding to 20 LEDs turned out to be a real challenge. I first tried cascading two CD4017 counters, expecting the second to pick up where the first left off. But synchronization issues meant only one would light, or the sequence would reset at the wrong time. After some trial and error, I found a better solution, using a CD4013 flip-flop. At the heart of the design is still the 555 timer. When you press and release the start button, the timer runs at a higher frequency, spinning the LEDs rapidly. As the capacitor discharges through the resistor network, the voltage to the 555 slowly drops, reducing the clock speed and causing the wheel to decelerate. The CD4017 receives each clock pulse and sends it to one LED output at a time. Meanwhile, the CD4013 flip-flop ensures half the pulses go to one group of LEDs and half to the other group, doubling my outputs to 20. I also used 2N7000 MOSFETs and BC series transistors to handle switching and level shifting, making sure each LED received the right current while keeping the control signals clean. As the circuit decelerates, you might wonder, how is the stopping LED truly random? Although the underlying logic is deterministic, the randomness emerges from several factors. First, the rate at which the capacitor discharges through the resistor network is subject to small variations in component tolerances and electrical noise. Second, and mainly, human reaction time. When releasing the button, it introduces an unpredictable delay. Together, these factors create a pseudo-random effect. Even though the sequence follows a set order, the precise moment when the wheel slows and stops varies with each activation. To give the wheel its iconic look, I designed a custom PCB in Easy EDA. I calculated that each of the 20 LEDs need to be spaced by 360 degrees divided by 20, an 18-degree separation, using polar to Cartesian conversions seen here. I positioned each LED footprint precisely around the circle of radius r. This math-driven approach made the final board symmetrical and visually appealing. After finalizing the PCB, I created a snap-in enclosure with Fusion 360. It fits snugly under the board, eliminating the need for extra fasteners. I would like to thank Evan Malcolm for printing this case on short notice and doing an excellent job, ensuring that I could snap in the board without any other fasteners. Very unfortunately, in a small PCB error design of the BC547, the E and B pin were fused on soldering, the downfall of the effectiveness of the final product. By combining classic ICs like the 555, the 4017, and the 4013, along with transistor-based switching and careful PCB design, I built a fun interactive game that showcases both digital logic and analog timing principles. Thanks for watching. I hope you enjoyed this look at my hardware-only roulette wheel.